So in this video, we're going to quickly review the idea of relative extrema from pre-calculus, and then talk about the idea of finding critical numbers. So relative extrema are always going to be defined in terms of open intervals. So if there's an open interval, if there is an open interval, and all a relative extrema is a maximum or minimum value of a function over an open interval. So if you can find some input value c for which f of c is the biggest it can be on an open interval, then you have a relative maximum, or also what's also called a local maximum. And if you can find an input value c for which f of c is the smallest output that's possible on an open interval, then you have a relative minimum. So graphically, from pre-calculus, what we were looking for are local high and local low points on the function over open intervals. So for example, for this cubic polynomial here, I could say, hey, look at the open interval from -1 to 1. So I could say let x run over the open interval from -1 to 1. And on that open interval, I'm going to have inputs and outputs corresponding to roughly this part of the graph on this open interval. And what we can see is that this is the highest point on the graph over just that open interval. So this is a relative maximum. So I could say, hey, f of 0 equals 0. So 0 is a relative maximum value over just this little open interval here. And then I could also look at the open interval from 1 to 3. So I run the graph from here to here, and on that open interval there's a lowest point on the graph. So here f of 2 equals -4. -4 is the smallest output on that open interval. So -4 is the relative minimum on the open interval from 1 to 2. So looking at the other graph, I can say, hey, make the open interval, let's say, from -2 to -1. So the graph is going to start somewhere up here. It's running down to about here over that open interval, and I can see that I have a lowest point on the graph over that open interval, and that lowest point on the graph over that open interval is the relative minimum on that open interval. I could then run the graph from, say, -1 to 1, and if I look at the graph over just that interval, there's a highest point right here, and that's a relative maximum. And then I could run the graph over the open interval, say from 0 to 2. And if we run the graph over that interval, we're going to get this piece of the picture roughly. And there's going to be a lowest point right here on the graph, and that's going to be a relative minimum. So relative extrema, relative minimum, relative maximum, the lowest and highest outputs on a graph over a given or defined open interval. And the key idea is that those relative minimums or maximums on a graph are going to occur in one of two ways. So a highest point on an open interval will either have a tangent line whose slope is 0. So here's a relative maximum. When I draw the tangent line to the graph at that maximum, I want to notice that the tangent line has a slope of 0. And here at this local minimum, if I draw in the tangent line there, the slope of it will be equal to 0. And because the derivative tells me the slope of the tangent lines, I know that the derivative of f is 0 right there. So the places where you get the x or input values that generate relative minimums or maximums on a graph are the critical numbers of the graph. So here I can see that this local maximum happens when x equals 0. So I know 0 is a critical number for this graph. And here I see that I'm getting a local minimum, a place where the tangent line is equal to 0 when x equals 2. That's a critical number for the graph. The key is, because the slope of the tangent line is 0 there, to find these critical numbers, all I would need to do is take the derivative and set the derivative equal to 0. So for example, this graph is f of x equals x cubed minus 3x squared. I could take the derivative, which will give me 3x squared minus 6x, and then I could say, when is the derivative equal to 0? And this one looks like it can be factored, so I get 3x times x minus 2 equaling 0. And then the zero product property would say either 3x equals 0 or x minus 2 equals 0. So either x equals 2 or x equals 0. So now I found the critical numbers of the graph by setting the derivative equal to 0, because that setting the derivative equals to 0 allows me to find the places where the slope of the tangent lines are equal to 0. We want to remember that the derivative is the function that describes the slope of all possible tangent lines. So critical numbers, places where the derivative is equal to 0. So when I look at the other picture, I have a local minimum here, I have a local maximum here, and a local minimum here. And again, the tangent line slope is 0 here and here. So I could find those by setting the derivative equal to 0. But notice this local minimum is occurring at a cusp. And we know that at the cusp, the derivative is undefined. So another way to find a local minimum or maximum is to look for places graphically where cusps are occurring. And the cusp are always going to occur when the derivative is undefined or doesn't exist. So when we're finding in subsequent videos, we're going to be looking for extreme values on closed intervals using the extreme value theorem. And so we're going to be needing to find places where relative minima and relative maxima occur. And these are going to be the two tools that we use to find the locations of relative minimum and relative maxima. They're going to occur at the critical numbers, and the critical numbers are going to happen when the derivative equals 0 or the derivative is undefined or doesn't exist. So for this function, I would need to know, hey, what x coordinate corresponds to the cusp? That's a critical number. What x coordinate corresponds to this local maximum? That's a critical number. What x coordinate corresponds to this local minimum? That is a critical number of the function.